All right, so this three-phase power problem. We have three phases, and the first thing I would do if I was looking at this is just write Y to remind myself that that's what I'm looking at. Here's a Y connection on the source side and a Y connection on the load side, right? Source, line in the middle, load on this side. Everything in this whole class is needed a source, it's needed a path to get to the load, and a path to get back, and a load that's taking it. Remember, if there is no load, that's a short situation, and but there is a load and there is a line impedance. You could box this if you wanted and say that this is Z line, write a J component on it, and box my load here, and that is a positive J component on that one. And then this right here, EAB, is going from line A to line B. So this is a line voltage. And I said, if not stated otherwise, it's almost always the line voltage is what's given. And that's because in the real world, I can easily put a voltmeter between two lines. And I can also see right here from line A to line B, right? And if phase means across an element, well, this is going across down to neutral and across another element. So it can't be the phase voltage, that's the line voltage. So if I'm you, the first thing I'm going to do is I'm going to draw a single phase equivalent. And the reason why we can do that is because we're in a balanced system. It may say it in the problem statement it's balanced, but what I could do is I could just look at all of these and say, okay, this one, all of my lines have the same impedances, right? They're all yellow right now. See the 2 plus 1J, 2 plus 1J, 2 plus 1J. Okay, and so then if I was making sure I had a balanced system, there's my lines, and now look at my load. My three phases all have 20 plus 10J, 20 plus 10J, 20 plus 10J. But the other thing is that this is EE 301, and so we always use balanced loads in this class. So because I have a balanced load, I can draw a single phase equivalent. Now remember, this EAN on this side is acting like a voltage source because it is an inductor labeled here, but remember on a generator, there's a spinning magnet inside of the coils. So there's the coils, the spinning magnet generates a current that we model as a voltage source. Inside of here, I have 2 plus 1J. On this side, I have 20 plus 10J. And on my source on the left, if this is A and this is N on my single phase equivalent, I need to divide that 208 into a phase voltage, right? So the equation sheet, make sure I write it down right, but it says V, does it say V or E? Yeah, V line equals V phase root 3 angle 30. So what I need here is my V phase, which is EAN. So I divide 208 angle 0, divide it by root 3 angle 30. And so on this, I now have 120 volts angle negative 30. Okay, so now I have this single phase equivalent, and now this current that I'm going to find is pretty easy. The current in this whole thing is everything's in series. So I say I, V equals IZ, which means that I equals V over Z. I'm looking at the total on this little circuit, and we'll call it, I'll just say total on this circuit real quick, right? So the voltage total, 120 angle negative 30, and the Z total on this is 2 plus 1J plus 20 plus 10J. Plug all that into the calculator, and I get 4.88 angle negative 56.6 amps. So that is for, this is IA, and that's also IAN, right? Which is on the source side. That was also I lowercase an on the load side. And on the equation sheet, it also says I line equals I phase. And that's pretty obvious to see on our single phase equivalent, that what goes on the phase through the element on the left is what's going through the line at the top, and is what's going through the phase on the right. Phase means element. So phase voltage is across an element. Phase current means through an element. So the current going through here, the current coming through here.
Sir, so is the line current the same as the phase current here? Because IA is the line current, and then IAN, like both uppercase and lowercase, would be phase currents?
That's correct. And this is a YY system. So if it was a delta, the currents would change. If you look at the equation sheet, it says the I line and I phase aren't equal. Actually, I'll just pull it up. Let's go the equation sheet right here. That's a great question. So I line and I phase are equal when I have Y connections. And since it's a YY, that means the phase on the left equals the line, and the line at the top equals the phase on the right. So now I have for IA, it says though, to find the line currents, plurally, be sure to find all three of them. So IB, right, it's a three-phase system, it's balanced, so they all have the same magnitude, 4.88 amps. It doesn't state, but we can assume positive phase sequence, which means I go minus 120 off of the negative 56, so I get 176.6 degrees. I'll make some space for IC. IC is 4.88 amps angle, and now I add positive 120, so I get 63.4. On the homework, you may have seen it subtract 120 again off of the negative 176 to go to like 296. But if anything goes past 180, the most correct answer is to bring it back. So if I think about the way a circle works, right, positive 63 is the same as negative 290, or whatever it would be, 296, right? So, no, 256. Am I thinking that right? Whatever that is, 176 minus 120, yeah, 296. But they would be the same spot math-wise. So on ours, we subtract 120 and add 120. Okay, so the next one says, determine the total real power delivered by the generator. So real power is P, right? And it's delivered by the generator. So that's on the source side. Okay, so what I'm asking for in part B, I'm asked for P total, and I'll say from AN. And the AN is because I'm looking at it on the total from the load side, and then I'm going to multiply by 3. So remember that P total equals 3 times the P of a single phase. Here's part B over here on the right. Okay, so P total is equal 3 times the single phase. Well, the single phase on the source side is capital A, capital N. So then I can plug in. There's multiple ways to do this. Let me think of. I want to make sure I do it right. Because what I would probably do if it was me actually solving it is I would do S equals VI complex conjugate. I'm looking at the solution that they have on the Jeopardy, and they solve it with I squared R, which also works. For me, I'm a big fan of complex power because then it gives me everything I need to know on that. So the VAN in this case is 120 angle negative 30. The IAN is 4.88 angle negative 56.6 complex conjugate. And then once I do that, it'll spit out my answer. And if I put it into rectangular, then the PAN that it'll give me is, I need to actually type it in my calculator. 120 negative 30, 4.88, negative 56.6. Actually make it positive 56.6. And I get, actually I'll just write both parts down. And I put it into the polar. So SAN is 523.62 plus 262.21J. So that is P and that is Q of a single phase. So now for P total, it's just 3 times 523.62. And I get 1572 watts. So that's the real power delivered by the generator. Now on the other side, it says total real power dissipated by the load. So part C is the power total from, and I'll say P lowercase an, because I'm looking on the load side. So look back, and I'm grabbing these numbers from my single phase equivalent. That's where I got the 120 angle 30. And I'm going to do the same thing over here. But because I know I and I know R, I'm going to use P equals I squared R, right? So I squared R, lowercase an, RAN. So the power, ANI, is that same 120. It's just the absolute value. If you look at the equation sheet, no, not 120, 4.88. 4.88 squared. The R from A to N, look back to A to N, the R is just 20. It doesn't include the 10J. And so I say 20, and then I multiply 4.88 squared times 20, 476.288. That's my single phase. So then my total that's been dissipated is 3 times that. And that comes out to 1429 watts. The last part says determine the load phase voltage, VAN, and that's easiest on the single phase equivalent. And if I look at this, I mean, this is basically, I'll put this in red, right? This is a voltage divider rule, or I could multiply IZ, VAN, part D, VAN, I could do IAN, which we know is 4.88. ZAN is all of those together. If you did the voltage divider rule, VAN would be the voltage capital A, capital N, right? Looking at that single phase equivalent. And then the ZAN on top. So 20 plus 10J. And on bottom, it's the Z total, right? This is with VDR. and that would be 22 plus 11J. That'd be the other way to do it. Either way, they both give you 109.1 volts, angle negative 30 degrees.
Which ZAN would you be using? Did we calculate that already?
Yeah, ZA, look at it's 20 plus 10J. Because it's just the Z between node A and node N.
So then wouldn't it be easier just to do the VAN is equal to IAN ZAN? Is there any reason why we would use VDR?
If you hadn't been asked for the line currents, it would be, like if you weren't asked for the line current, you could quickly find the load voltage is all I was pointing out.
Oh, okay. Thank you, sir.
Yep. But yes, the faster way probably would be 4.88 angle negative 56.6 and 20 plus 10J. It'll get you the same answer. All right. Questions on that?